few moments to get started. Yeah, so just to kind of, and indeed this doesn't work for me, so maybe we just use V-stick approach. Yeah, as we get the sort of technology set up, just to sort of complement Suzanne's introduction, I don't claim to be an expert on any of the things I'm going to talk about, but one sort of nice thing about being a writer is that when you're doing research for a novel, you get the opportunity to talk to a lot of interesting people from different fields, and do a lot of reading around the themes and topics of your novel. And my third book is indeed going to be dealing partially with games, in fact games with quantum elements in them. And actually I am thinking now that probably my next novel after that is going to be about crowdsourced science or citizen science. So I've had the opportunity to do a bit of thinking around this topic, and sort of the viewpoint I've oh dear. So what I'm going to kind of try to give you glimpses of are the concepts that I found to be useful. I'll try to relate them to the topics we've talked about. So I'll try to talk a little bit about game design. And apologies to people like Judy and Sandy, who probably know much more about that. But hopefully it'll sort of seed the subsequent discussion a little bit. How are we doing? Okay. So we'll see how the slides will come out.
Yes.
Okay.
There's some problem with the light. Somehow the connector maybe. I think if there is a bad connection between these two, it's sort of, you see there, other kind.
There's some quantum fluctuation going on definitely over here. Okay, so kind of just to conclude the introduction, you should always regard writers as thieves. We steal ideas from other people and try to weave them together into a coherent narrative. So a lot of the ideas in this talk come from these people: Ralph Koster, Greg Kostikian, Greg Turfree, and Michael Nielsen, and others. I'll try to acknowledge them as I go. So we've already mentioned several times the rise of games. So here I'm displaying Angry Birds instead of Angry Nerds for sort of patriotic reasons. I'm originally from Finland. Jacob actually already mentioned the sort of orders of magnitude of effort which are going into games globally at the moment. So I'm not going to repeat that, but just to give you one illustration of the order of magnitude of things. The hours of Angry Birds played per annum are about 1.2 billion, and all of Wikipedia so far, I think in all languages, actually not just in English, has approximately taken 100 million person-hours to produce. So basically, the same effort as with Angry Birds, we could produce 12 Wikipedias per year, just Angry Birds. Globally, we have at least 1 billion gamers, a gamer here being defined as a person who plays at least 13 hours per week. So if we multiply that by sort of the computational power of 1 billion human brains, we end up with quite a big number. You can argue about what the computational power of the human brain is, and part of the question is what is it actually good at. But certainly there's a lot of untapped resource there. Of course, this is not a new idea. In fact, something I want to highlight is that until relatively recently, all computation was human computation, and people actually developed fairly elaborate frameworks for sort of splitting things into small modular components and handing them out to smaller groups of people to solve. One of the first people to think about this in kind of more formal way was actually Charles Babbage, of course, sort of better known as the father of the difference engine and the never built analytical engine, and sort of forerunner of our modern computers. And so Babbage actually looked at how sort of the large computing organizations of his day like the Royal Nautical Almanac operated, and he describes them and analyzes them in some detail in his writings. And and what's actually quite apparent is that a lot of these institutions worked quite a lot like the Amazon Mechanical Turk. So they kind of had a sophisticated system for dividing computations into discrete tasks and announcing them and allowing individuals to bid for them and actually compete. So already there were quite a lot of game-like elements there. And so there is actually now sort of a growing interest in revisiting some of the techniques that these very old human computation organizations developed and seeing maybe if they could be used in some of the problems that we were talking about. However, Babbage wasn't happy with how these organizations operated. He thought there was far too much error. He came up with various error correcting schemes, but ultimately it was that sort of gave him the impulse to start working on the difference engine. So in that sense, we are now coming a full circle. So I think Jacob and I quite successfully played the ESP game with this slide. So I'm not going to say too much about the sort of current efforts in these fields, except maybe to point out that in addition to all the frameworks and games that Jacob already mentioned, there are other ways of sort of leveraging the kind of more available power of individuals without necessarily a scientific background to solve difficult problems. I mean, there are various incentive schemes. There are commercial websites such as Innocentive that actually present scientific and design challenges with sort of financial prizes attached to them that sort of can be deployed to a community of non-experts who just might have this sort of micro expertise that is required to solve the problem. There have been challenges like the Red Balloon Challenge of DARPA, where sort of basically 12 balloons were placed in random locations in continental United States, and people were sort of challenged with the task of creating a framework that would allow those to be discovered as quickly as possible. And there was a big cash prize again. So just to highlight the fact that not only games, but sort of the general power of internet for community formation and sort of different incentive schemes do allow other possibilities to tap into this sort of at least 1 billion collective of human brains. So I think Jacob also quite well divided the current efforts into different categories. So a lot of the best known ones like Galaxy Zoo and Zooniverse indeed have to do with big data and looking at enormous data sets and doing some fairly trivial tasks. But hopefully we will find ways to also move more into the folded style hard problems and hard fun, and I'll come back to that a bit later on. But so by now we have seen enough examples of these kinds of things that it is possible to sort of start to analyze what actually makes them work, what leads to successful citizen science projects. And the best book I've read on this topic, which I highly recommend, is Reinventing Discovery by Michael Nielsen, who sort of goes through a whole raft of different sort of online collective intelligence environments, starting from sort of this famous chess game of Kasparov versus the world, and several others, and he sort of quite well identifies some common factors for the successful ones. So first of all, you need to have some sort of feedback loop. A participant has to be able to get an estimate feedback on how successful their action, whatever that was. It has some sort of underlying architecture that allows the participants to direct their attention to where they can do the most good. That sort of the information doesn't overwhelm them, but allows them to discover the topics they're interested in and where they can contribute. The domain should allow some sort of micro expertise, some sort of narrow domain or a set of techniques or heuristics that an individual can easily discover or sort of can really uniquely contribute to. And we already several times mentioned the fact that problems need to be modularized so that they can be worked on by individuals or separate teams. People should be able to make even small contributions, sort of Wikipedia style, where a lot of the most participants actually make just 1 or 2 edits to a web page. Something that's very important is also the ability to build upon earlier work. So you should be able to see the kinds of solutions others have done, take them, play with them, modify them, hack them, and then improve them. Now, a problem we've also already encountered in the great descriptions we had from Sandy and Judy about and Suzanne and Oliver from the sort of various communication difficulties. One requirement also is that there has to be some sort of shared praxis, some sort of shared understanding of concepts, of a common vocabulary in the collective. Although you also need cognitive diversity, so that you just don't just end up with an echo chamber. And I think quite a lot of these things, pretty much all of them, can be found in online multiplayer games. So certainly there is, so games do offer a very interesting platform to start to go in this direction. Foldit has been mentioned several times. Something I'll highlight without going into too much detail was that there was recently a very good report on the actual process of design of Foldit and how it became successful. And the key thing was really this sort of very tight feedback loop between scientists, the game development team, and players. So rapidly trying out different things, trying to accurately translate the scientific problems into game mechanics that were engaging and interesting, but didn't sacrifice the sort of fidelity to the actual problem that was being solved. So I refer you to this article, The Challenge of Designing Scientific Discovery Games, by Cooper, plus 57,000 Foldit players. But I think it does highlight sort of the challenge that Sandy and Judy also talked about, that it's not just a normal game design challenge that you're facing with scientific games, that you need this balance between sort of working on the actual problem and making the game engaging enough. So what about quantum citizen science? What could be? I mean, is there room for quantum scientific games? Obviously, we've already heard about two very fleshed out examples. But to sort of take a step back, what are the bigger questions that we could address in this context? The first one was already mentioned. I mean, can we figure out what human beings are good at, or what collectives of brains are good at? I mean, that's a very, very wide question, I think, made more difficult by the fact that now, when we talk about multiplayer online games, we're not talking about just collectives of human brains, but we're talking about some sort of collective of human-computer hybrids. I mean, the architecture you create and the tools you provide the players with, in other words, the game design, probably really influences the problem space that you can tackle. So maybe those kinds of collectives can tackle problems that individual humans are not good at due to limitations of visualization or whatever. Now, obviously, it was wonderful to hear some of the feedback from the students that Jacob talked about. So clearly there is room for educating the public and maybe sort of demystifying quantum mechanics a little bit through games. And then there's sort of possibly, given the success of the sort of Zooniverse style projects, perhaps there are some big data style problems that could be tackled as well. There's one project that I was able to find called Feynman's Flowers, which sort of tries to figure out magnetic properties of nanostructures and different molecules based in Imperial. But it is still kind of in this domain of sort of trivial fun, there's obviously, we've already heard that it is possible to start also gamifying directly research-related algorithmic problems. But just to throw in one more big question, the thing that struck me the most when I started thinking about this topic was that was kind of the analog between the really unexpected things discovered by these sort of collectives in domains that require true creativity and sudden insights from unexpected directions, was that we don't really have great uses for quantum computers yet. I mean, we have some ideas, But essentially we have two good quantum algorithms. We have Grover's search and we have a quantum Fourier transform. And everything we know is kind of applications of one or the other. We don't really even have a definite proof that quantum computers are fundamentally more powerful than classical ones. I mean, we believe that they are, but there's no definite proof of that. Even prime factorization might end up being feasible with classical computers, who knows. So what I started wondering about was, would it be possible to create possibly simulated quantum systems for people to play with, to sort of crowdsource this problem of discovering interesting things to do with quantum information? Not necessarily full-blown quantum computers, but perhaps some more limited quantum systems, or very modest scale quantum computers that we could simulate. So this sort of idea of let's leverage this collective intelligence to actually really find new research directions, for me is potentially the most exciting one. So how would we go about this? I mean, obviously we've the two previous talks were about two specific problems that were converted into games. But when you sort of search for quantum and games, this is kind of what you discover. I mean, you come across sort of a quantum mechanical versions of game theory. Now, of course, game theory is really more about economics and decision making and some very, very limited scenarios than the kinds of games that we're talking about. But so the most famous example perhaps is the quantum prisoner's dilemma. So everybody's probably heard about prisoner's dilemma. So this iterated game where you have to decide if you're going to rat out your sort of fellow criminal or not, and you have essentially an incentive structure where if you cooperate, you could both go free, but there's always an incentive to not to cooperate. And it turns out that if you allow the players to, in this game, to share an entangled state, they can actually do better than the classical version. So they can actually cooperate better than in the classical setting. However, it's not ultimately very satisfying, because you could regard this version of the game just as a sort of a classical extension of the original game. It sort of essentially changes the game into something completely different, and you could do that transformation using other ways. I mean, it's not truly quantum in that sense. There is another class of sort of really more truly quantum games called pseudo-telepathy games, which were actually invented for sort of educational purposes. So to give very simple illustrations that things happen in the quantum world which are classically impossible. One of these things is the thing here on the right, which is called the Mermin magic square, where essentially two players have to fill in this square, one on the column and one on the row, in such a way that the square where they intersect has to have the same sign, and there has for one player the product of the column has to be odd, and for the other one it has to be even. And basically this is classically impossible if the players are not allowed to communicate. But there is a quantum solution to this game. So there is this kind of there is this whole class of games where or sort of game-like demonstrations where the players can do classically impossible and totally counterintuitive things. There are similar things to do with graph coloring. So I'm sort of mentioning this just to illustrate that people have thought about game-like and puzzle-like settings in the literature quite a lot already, but not really in the context of computer games. I mean, well, there are a few computer game experiments as well, but mostly in the sort of style of simple demonstrations or research projects. So there's something called quantum soccer, which reminds me a bit of your sloshing potential well. There is something called quantum core wars, which is sort of like a quantum artificial life simulation. And there's a few others, but they're not really that much fun to play, and don't really sort of give you this addictive fun aspect of things very well. So, how could we really create engaging and interesting games or quantum games for research to answer any of the questions I mentioned earlier? And I thought to make some progress towards that, it might actually be useful to try to give a brief definition of what games are, or what sort of one school of game design thinking thinks of them as. And so my favorite resource for that is a book by Ralph Koster, which called A Theory of Fun, which is kind of invisible in the margin there. But what Koster basically says is that it all has to do with how our brains work. So what our brains really do is that they eat patterns, a bit like Pac-Man. So we look at our environment and we interact with it, and we try to find patterns in it. If we find one and use it successfully, our brain sort of rewards us with a little rush of dopamine. So it's fun. And we try to chunk things together into these sort of kind of a symbolic representation that becomes almost, use of which becomes almost automatic. And games are very good at generating patterns which have some sort of underlying order to them, and our brains really like that kind of performance of just being able to discover the pattern is just hard enough, like we were talking about earlier, and which keeps you at the edge of your ability constantly and sort of creates this sense of flow. So what games really are fundamentally are teaching machines, or perhaps science machines in some sense, if exploring this sort of artificial game reality. And our brains adapt to the game environment very quickly, and very quickly start to see only the essential patterns in it. Now, of course, people talk a lot about the sort of effect game violence and sort of the I don't know, sexist or violent content in games has on development of children. But something that Koster points out is that gamers tend to completely abstractify all that away when they play. So when you play a shoot-'em-up game, you don't actually think of it as a violent act. Your brain starts to think of it as this abstract action where you discover the pattern, perform the right action, get the right feedback, and it's actually all the sort of blood and gore and guts is eventually quite quickly filtered away. Now, of course, that may have some negative effects, but the point is that there is actually a huge difference between the surface of games we see and the sort of the pattern generation engine that's grinding away underneath. And as we play, that's what our brain actually gets more engaged in rather than the surface. And the surface stuff, the story and score and all that, they're just actually different feedback mechanisms for our brain to use to learn the underlying patterns. Anyway, many people may disagree with Koster, but I quite liked his thinking personally. Now, to make that a little bit more formal, which is now kind of distorted completely. So this is all these are supposed to have labels. I think the PDF is not being properly rendered, but the I actually need to see this. Okay. My point with this the point with this diagram was to illustrate what could be called sort of a basic game building block. So, okay, that's not very useful. So, I should really.
You have the keynote version.
No, it's a PowerPoint version.
Okay.
But you're using Open Office. I see.
I do have PowerPoint on my Mac.
Ah, right. That might have been better. Well, the okay. If you don't mind, I'll sort of keep talking. So the point of that diagram was that you can think of games as being sort of made out of other games. I mean that each game has a bunch of sort of basic mechanics that you put together, and they all have roughly the same structure as in the diagram that you'll hopefully see it in a moment. It's really just a simple feedback loop. You have a mental model of the game. You perform some act of preparation before you actually perform your action. You act upon your world, you get a feedback, you modify your mental model, and this is the loop you iterate. Now, of course, that sounds awfully simple, but in a typical game, you actually put several of these things together, and the play aspect, the sort of gaming aspect, is really the interaction, or rather the slack between these mechanics. In what sort of interactions can you find for these mechanics? That's kind of the exploration and the play aspect of things. So
we are almost there. Sorry.
no, it's okay. It's okay. So that's actually, I mean, I mentioned that because games have been described as systemic media by game designer Eric Zimmerman, amongst others, and he really highlights the fact that actually the ability to play games is almost like a new kind of literacy, because games are by their very nature systemic. And we now live in a world of hugely complex systems with lots and lots of interacting components. It's actually really games that sort of provide a good medium for exploring that world.
I don't know if.
Okay. Well, I think I've already I've already sort of described the diagram, so we can just keep going. I think a lot of the other diagrams seem to be messed up as well, but. Okay.
Oh, sorry, I don't know.
Right. So anyway, these are the sort of things that.
No. Okay. There is some problem.
Okay. Now it's in some sort of presentation mode.
Yeah.
Yeah. So these are sort of. One of the approaches taken by game designers is taking a lot of these known ludemes, these game basic building blocks, and putting them together in new and interesting ways to sort of get the effect that you want. And actually, yes, sorry.
Can you say a similar thing about writing a novel?
Yes, of course. I mean,
it's sort of like the template sort of romance. Stories which have been retold and retold and retold.
No, of course that's right. I mean, I think in every form of art, you could say that there are certain basic forms that you combine and recombine. I'm sure music is exactly the same. I would say games are probably even closer to music than writing in that sense, because here the point is that the underlying ludemes, they are actually quantified. There is actually a formal definition of the underlying mechanic, whereas I think in writing it's a bit looser than that. I mean, there are genres, archetypes, certain plot structures that recur, but they're not quite as formally defined as I think, because actually in games, computer games, you can write actual code that implements your mechanic.
So can I just ask a quick question?
Yeah.
And so do you think then that quantum game or citizen science games needs a new system then of categorizing games?
No. I think
directly.
No. I think that fits. I think they fit exactly this scheme. I guess what my main thrust is that in order to make interesting and engaging science games, we have to find the ludemes, the new basic units that we can then inject into this process of game design. The question is, what are those ludemes? They're probably different for all these different research questions I used. So, what sort of new game mechanics should we introduce to, and how should we? Can we recombine them with existing mechanics in interesting ways to create games which both serve the research purpose and are engaging and fun as games? But I'll sort of come to that and indeed that's sort of the way pretty much all the puzzle games and computer games and other types of games have evolved in general. That people have sort of started, people have taken an existing game and started adding new elements to it. So you can actually, and Koster actually has a nice diagram where he sort of traces the evolutionary tree of shoot 'em up games, like 2D shoot 'em up games, and how they sort of went from your sort of space invaders to sort of really complicated hyperkinetic console games and arcade games that of sort of, I guess they reached their peak around 2000 already or something. But so I think in the case of quantum research, we have potential, I think, for a lot of really interesting and bizarre game mechanics, as sort of illustrated by the example of this magic square, and we can maybe think of others. So how are we doing? Okay, we'll just. I think we covered that. I think I covered this slide to illustrate the underlying abstraction. I talked about that. I will mention something about this slide. So the there's something we already touched upon in the earlier discussion. So in many games are fun in many ways. I mean, there's sort of, and I think it is interesting to explicitly categorize them. So we have easy fun, which is sort of, I mean, it could just be aesthetic appreciation, or it could be sort of performing a task that immediately gives you the easy solution. I mean, you could argue that watching movies or reading novels is kind of easy fun in the sense that you don't actively have to do very much. We also have fun by altering our physiological states, whether by drinking or enjoying other activities, or sort of playing very adrenaline-inducing games that actually make our heart beat faster and sort of give us this sort of visceral thrill. Multiplayer games have been mentioned many times, and we really are social animals, so we have fun whenever we interact with other people. But maybe there is something to be said for this element of hard fun, of sort of really hard problem solving that pushes us to the edge of our abilities, and that's maybe where sort of the real meat of scientific games may lie, but it has to sort of be taken in the context of all these others. So actually, just to continue on the theme of hard fun, people actually now have a fairly solid understanding of what sort of problems can already be solved in games. I mean, recently there has been an awful lot of formal complexity theoretic analysis of computer games. Sort of Harn and Demain have a whole book recently on that. You can in existing computer games you can find some classic NP complete problems. For example, it turns out that assigning your sort of team members to attack an enemy in the right combination and defining the right interactions can, in MMOs like World of Warcraft, can actually be interpreted as solving a graph isomorphism problem. All kinds of resource allocation games translate to the exact cover problem, and there's many other examples. Pac-Man, which I've mentioned already, turns out to be equivalent to the traveling salesman problem. So clearly, players who play these games are already solving some quite hard problems. Whether or not they are doing it better than computers are, then that's a different question. Are they better at finding the right heuristics or the underlying structure? But that's part of the conversation. Something I did notice actually was that a lot of these types of problems are not necessarily using our spatial intuition or our geometric intuition, but actually our social intuition. I mean, a lot of these kinds of problems occur in massively multiplayer games like World of Warcraft. So I think it's possibly quite interesting to think about also other uniquely human cognitive abilities than just sort of our ability to visualize, which we already noted was kind of vulnerable to biases. So just I've kind of already touched upon what I was going to say about game design. So how does game design work? Well, you take something that's fun and you reverse engineer it. So you try to create an incentive structure for a player that makes them do an activity that is fun and creates the feeling we want to evoke. In that sense, it's almost completely opposite to writing fiction, where you actually try to project the reader into somebody else's head. Whereas in a game, you try to get them to do something, and it's the act of doing that makes them experience the emotion. Now, because we are in sort of a technical audience, I will mention the fact that there is actually now quite a lot of work on formal models for game design. I mean, people are starting to use and actually develop software tools for based on things like Petri nets and constrained logic to actually define interactions between basic game mechanics and already sort of try to show in the sort of pre-design stage almost that certain combinations don't work very well. So an exercise for those who are interested, can we develop a quantum version of these frameworks? There certainly are quantum Petri nets, and could there be quantum constrained logic that would allow us formally analyze combinations of different game mechanics? That's another possible research project. But as I already said, the approach I personally got exposed to recently, which I thought worked quite well, was really this hacking approach. So let's just hack games. Can we take, if we want to do something new, is there an existing game that is kind of in the same ballpark? Can we add a new game mechanic to it and hack it in some way to get it to do what we want? And after that, do this rapid iteration of playtesting and refining and really failing as fast as possible until we discover something that's fun. Now, of course, as I already said, in the context of science games, we have the additional constraint that we have to represent the underlying science and the underlying problem faithfully. So that's in some sense much more difficult problem than this one. But still, I think this it's fun to think about this approach of game hacking or changing existing games. Just to sort of illustrate a little bit about what I mean by that. So a lot of the inspiration for this talk actually came from a game design workshop I was at in London last year, run by Greg Treffry, quite a well-known game designer, who sort of was quite a strong proponent of this approach. And he actually made us do, the sort of participants to do an exercise where the idea, so first of all, we played a game, which is always a good way to start any workshop, and I think people should do more of that in general. But and the game was called Zombies, and the goal of the game was to get you evoke the feeling of being in a zombie movie. We could actually play it later; it's quite fun. But the way it works was that basically you start out with one zombie, everybody else is just a human, and it's a turn-based game. So zombies and humans take turns. On their turn, humans can take one step, and zombies can take 2 steps. And if a zombie touches a human, the human turns into a zombie. Obviously, their brain gets eaten or whatever. You can see where this is going. Humans are going to die out very quickly. And the effect that is created in the end is the lone human left with this horde of zombies slowly converging towards them, and it was quite powerful actually, very combination of very simple game mechanics familiar from sort of childhood playground games. So then we were given the task of can you hack this game to evoke a feeling of friendship and altruism? And so we went through several iterations, and what we ended up doing was introducing a new mechanic that allowed human beings to pair up and kill zombies. So there were 2 groups of humans that started on the opposite sides of the play area, some zombies in the middle, and so the humans had to go and sort of find their soulmate. And so the zombies obviously would try to stop them, and it created a completely different game. Essentially, at first you would be sort of trying to flee from the zombies, and then you would find your soulmate, and it would be this sort of incredible rush of sort of empowerment. And I found you. This is it. Now we're going to beat them. So I mean, it's a silly example, but I thought it illustrates this process of taking an existing game and hacking it quite well. And I thought as an approach it was quite powerful. So to move on from zombies to quantum games, the question, of course, is what sort of basic quantum mechanics quantum game mechanics could we have that we could inject into existing games, either to address research problems or to make headway towards any of the other goals that we mentioned. I mean, there are many things. I mean, The sort of most fundamental strange quantum property that all these pseudo-telepathy games are based on is entanglement. There's also the fact that things are in superpositions, things are kind of fuzzy. There's the act of measurement. All these things could be used. And perhaps one question I have in general, perhaps for the physicists in the audience, is how hard is it to simulate a modest-sized quantum computer? How many qubits could be simulated in a classical computer so that we could create something that people can actually play with? Perhaps to be discussed later. But I thought I'd sort of finish with a bunch of examples of just really non-exhaustive list of games that we could potentially hack. I will go through them quite quickly. One example which already is kind of a hacked game, and I think illustrates very well this principle in the context of physics, is a game called A Slower Speed of Light, developed at MIT, which is sort of already a amalgam of first-person shooter and Pac-Man, which we always seem to be coming back to Pac-Man, and where you sort of move around in this beautifully designed game area, and you eat these spheres. And as you eat these spheres, speed of light slows down. So you start to directly see relativistic effects around you. Sort of you see red shift and blue shift, and you start to see Lorentz contractions and all kinds of bizarre stuff starts happening. And it's actually, after a while, it starts to feel quite natural that this is happening. So I thought it's actually quite a good model of this process in sort of the other big area of modern physics, if you like. And one question is, could one do something similar, perhaps even using this engine, because which is freely available in the context of quantum games. One interesting game which came out recently, which definitely incorporates the multiplayer aspect in different ways, is called Curiosity. So this came out. Famous British game designer of Populous, whose surname I can't pronounce, Peter Molyneux. Yes, that's right. His company recently released this game, and so essentially in the game, which you can play on iOS devices and so on, is you're looking at an absolutely enormous cube, really enormous cube, which is made out of smaller cubes, and the only thing really you can do in the game is to sort of chip away at these little cubes. You can buy, using real money, various tools that allow you to destroy them faster. And the sort of cube has layers and layers and layers and layers, and different pictures and hints and things are revealed at each layer. And the sort of primary motivation to play this game is that there's a secret inside the cube. Which hasn't been revealed, but supposedly will completely change the life of anyone who gets there first. And I think it's quite an interesting example of where you could imagine player teams forming. Everything is allowed. You could potentially try to create some huge collective that tries to get there first, or whatever. I mean, it's a bit limited in terms of the actual game mechanic. But I thought maybe I had some sort of Schrödinger's cat images in my mind, but I thought this act of sort of chipping away at something to discover something inside is sort of an interesting metaphor for something you could perhaps do in quantum in the context of quantum physics, where you measure things and then you destroy something about them at the same time. Some other examples. I mentioned very briefly quantum core wars. So that's kind of it's already an example of something that somebody has tried to take forward. But so Core War is perhaps one of the geekiest games of all time. I mean, really the most nerdy game imaginable. But it has quite an interesting fundamental concept, which is the players write programs for sort of a simulated computer. And the idea is that your program has to completely fill the memory of this computer, so destroy all the other programs or outcompete them or whatever. So it's kind of an competitive artificial life game in some sense. And people have discovered really strange strategies for playing this. I mean, there are all kinds of traps and things called vampires, which sort of modify other people's programs and all kinds of crazy things. And the ingenuity, even sort of very, very small hardcore community playing this game has displayed over the years is really incredible. So I couldn't help wondering, could we, referring to my earlier point about how could we figure out what to do with quantum computers, could we really have a sort of a proper quantum core war, perhaps with nicer interface and nicer nicer graphics, but something along these lines, which is actually kind of related to this game, which hasn't come out yet, called 0x10C from the developers of Minecraft, which I'll also talk about, where you will be piloting a spacecraft, where you will have access to a fully programmable simulated computer of the spacecraft that will allow you to sort of allow you enormous latitude to get the spacecraft to do all kinds of automated behaviors and so on. So that's kind of already perhaps going in that core war direction. I mentioned already all these NP complete problems that occur in MMOs. So World of Warcraft and its many relatives are perhaps an interesting example to look at. I mean, not only they have sort of the 3D world gameplay, combat aspects, but they have all kinds of things like in-game economics and complex team formation things and strategy and inventory management and all kinds of things where you could imagine doing very strange things with quantum effects. I'm also mentioning this because in my novel, this sort of future quantum game society actually evolves from World of Warcraft guilds, but that's another story. So I mentioned Minecraft several times. So if you don't know Minecraft is this game, sort of like a sandbox game where you it's a first-person game, but you do have the ability to build things. It's essentially like a physics engine with Legos. And it has other game-like elements like enemies and constraints and so on. But the main thing is that you can really build enormously complex things in it. And that's a computer. That's a computer built inside Minecraft. That's a programmable computer. And people have done even crazier things within Minecraft. Minecraft has things that allow you to build circuits and sort of complicated arrangements of levers and pulleys and things that interact. So it's not impossible to imagine some sort of quantum Minecraft that would allow people to experiment with quantum circuits or sort of other quantum physicsy things. In fact, people in Minecraft forums have already talked about this, and there is here is the sort of a dual wave particle experiment or double slit experiment with chickens implemented in Minecraft. Although I think it's actually a fake, but they genuinely have like a chicken cannon which you can build in Minecraft, shooting things at this sort of double slit and then looking at the distribution of the chickens coming out of it. So no matter how crazy the thing you are imagining at the moment is, it probably already exists in Minecraft. And finally, I'm going to conclude with Angry Birds as one possible example, again for patriotic reasons. But if you think about what Angry Birds really is, it's all about defining initial conditions for a physical system and then watching it evolve and watching interesting stuff happen. And I see no reason why we couldn't do exactly the same thing with the quantum system, provided, of course, that we get all the other wonderful game design aspects of Angry Birds right. So that's kind of pretty much concludes my talk. I mean, something I want to emphasize is that, as I mentioned earlier, games really, when we play games, they really modify our brain. They change us they give us new patterns to discover and teach us new behaviors. So they really shape how we think. So in general, we've seen how technology has shaped our society for the past few hundred years, and will do so. And one really interesting question is, what will sort of mature quantum information technology do to our society? As a writer, I think that's a a science fiction writer, that's one of the most interesting questions in the next 20 to 50 years, I think. But already, I think games or quantum games could offer us a laboratory to try to find out, and hopefully it'll be fun as well. Thank you.